Our final year project is smart shoes for exercise tracking and fall detection. People do activities every day, no matter indoor or outdoor activities. Walking and running are the most basic forms of exercise. Logging daily activity and tracking exercise time are important when people want to know their exercise habits. Also, gait detection and analysis can help prevent injury and fall during walking and running. However, traditional shoes cannot provide any valuable information for owners. People can't know how far they have walked by looking at these shoes. Current methods of exercise tracking are furnished by applications on the smartphones or smartwatches. Common functions include step counting, walking and running distance recording, exercise time tracking. These devices are not fixed on the feet, but wear on the wrist or put in the pocket. Therefore, they cannot record specific gait events and do analysis. Some researchers use camera-based systems to capture 3D motion. Force plate data that measure ground reaction force are also needed to supplement gait analysis. Although this method can do gait analysis, these equipments are limited to laboratory environments and cannot work for outdoor environment. Also, they are relatively expensive. There are some smart shoes in the market with built-in sensors and semiconductors, which can analyze users' gait and keep track of users' daily activities. However, you need to wear the particular shoes to get the detail. It's not work for random shoes. This project will introduce a wearable device that can be attached to human body, LPMSB2. This device can monitor users' exercising states and process data to perform gait analysis in real-world conditions. It's a wireless device with tiny size, which can perform high-speed and accuracy tracking of users' movement. It is composed of a gyroscope, magnetometer, and an accelerometer. With these three sensors, it can measure orientation and acceleration data around all directions. Additionally, temperature and barometric pressure sensors allow accurate determination of its altitude. It can communicate with the host system by Bluetooth. Maximum data transmission rate is 400 Hz. First, gyroscope, accelerometer, and magnetometer will collect data when using this device. An extended Kalman filter will be applied to the data in order to get more accurate results. Then, real-time calculation will be done to this data to get the orientation and accelerations. This data will be transmitted to computer by Bluetooth. Data will collected by inviting different participants to perform different daily activities. In order to obtain more accurate gait data, the device was attached to user's ankle. User will do some common activities, including walking, running, and stay still. Participants should do these activities on the natural scale, indoor and outdoor respectively. There are periodic patterns in these rhythmic activities. We can categorize activities into three groups: walk, run, and rest. For the same foot, it was assumed that the time interval between two steps is around 1 second when people are walking. When people are running, the time interval between two steps is less than 0.5 seconds. If there is no significant change in acceleration data, then it would be considered as rest. First, we let participants wear the device on their ankles during walking. The sensors on the device collect data based on the movements. From this figure, we can calculate time difference between two similar waveforms is around 1.2 seconds, which is satisfying the working requirement, so we can classify it as working. Another testing case is running. The average time difference between two similar waveforms is around 0.5 seconds. Then we can classify it as running. If it's rest, then all data remain unchanged for a long time. In gate cycle, initial contact and toe-off events are two important phases for gate analysis and identification. By visualizing sensors data and obtaining the waveform of the accelerations between steps, the initial contact and toe-off events can be identified. Ground contact time can be calculated as the time difference between toe-off and the initial contact. Observing this figure, active and inactive intervals can be clearly distinguished. For walking, ground contact time is around 0.4 seconds. For running, ground contact time is around 0.2 seconds. In this work, we have introduced a wearable device that can keep track of users' steps and gaits during different activities. Unlike those methods in the laboratory, our device can monitor the detailed gait events outdoor at any time. Currently, we invite participants to wear the device on their ankles. It can successfully simulate gait and transmit data to the computer. Users can easily identify the activities and know how they work by using this device. In the following days, we expect to further test our device and evaluate the performance. We should invite people in different age and gender to wear our device and test the device when users doing different activities, including going upstairs and downstairs. Also, we should develop algorithms to analyze gate data and implement 4 alarm function.